Welcome everyone to Gems from the Wisdom Traditions. This is our week of curving space, carving space. And it's a rather mysterious topic. And I began considering the idea of presenting it myself until I really began doing the reading for curving space and realized I just wouldn't be up to the task. And so I am so delighted that a very dear friend of mine was willing to make time for us. She is infinitely also more qualified than I am to do so. This is a person who has taught junior high school science for decades. And she was a neighbor of ours when our kids were growing up. And I think it is thanks to Kim that some of them made it through their math and science classes because when I couldn't tell them what to do, I said, just go talk to Kim. And she was always there for us. Tomorrow will be Pi Day. It's Albert Einstein's birthday. And so this topic arises out of that fact. And I was just thinking about how few of us actually can make any sense of what Einstein taught, or we haven't been able to do it on our own. So Kim is probably feeling unqualified for speaking on Einstein, and yet I feel that someone who is used to making science accessible to teenagers, probably, if she notches it down a few levels, might be able to make it accessible to us. Kim has done wonderful things with students in her classes. She's often given the least advanced students because she knows how to explain things so well, and also the most advanced AP students. And she's done a lot of special projects with them. I'd like her to just mention those before she launches into giving us a little starter on this conversation on curving space and carving space.
Renee wanted me to talk about some of the things we've done in school with kids. And, it all comes from not being afraid to sit alone at lunch because, and that's what I tell my students too. I was at a physics conference for teachers and at the Kavli Institute of Theoretical Physics here in Santa Barbara is sort of a think tank for really advanced theoretical physics. And part of their mandate is to include teachers with some of the conferences so that the effluva of the conference can absorb down into the general populace a little bit through the teachers. So if they're doing some big brainiac thing, some amazing theoretical conference on like biophysics or whatever it might be, they'll have a conference for teachers. And so I was at one of those conferences, which was about, I think it was about the Hubble Space Telescope. And there was a lunch line, and I noticed that many people had kind of clustered around friends that they already knew. And I just decided, well, I'm going to go sit at that empty table over there and just see who comes. And so who should sit down but some nice British people, and they were talking. And anyway, it turns out I complimented them on their accent. It turns out that one of them was the director of the Falk's Telescope project in Great Britain, who was basically in charge of these large 2-meter telescopes in Australia and Hawaii to control, let students control the telescopes, robotic telescopes, via the internet, and plan a target that they want to look at. And then they could actually on the webcam see the telescope moving and see the dome moving out and take their images of a star cluster or a field of whatever they wanted to image. And then they were taught how to process those images using simple, freely available software on the internet, and actually get some real research done too. through some guidance from the Falks Telescope Project. And this was all conceived by a man named Dill Falks, who was financially able to do this, set this up. And it's ideally located in Great Britain for their time slots of when they're in school. The kids at a normal time when they're in school can, everybody, let's get on the telescope and move the telescope in Hawaii and go see what's out there. Anyway, I ended up talking with them and became Facebook friends with the director, and just kind of casually kept in touch with him. And then years later, he said, I asked him a question, and he confused me with the teachers that he was already working with the telescope project. And he said, well, when you have your telescope time, you can, do the X, Y, and Z. And I said, well, I don't have my time, actually, could I? And so we became the first American group with the British group of kids using the telescopes. And so the first time we used it, we had to get up at like 5 a.m. This is before our school had reliable internet. And we went to the Starbucks that's near our junior high school in the Fairview Shopping Center at 6 a.m. and logged on, like, had the power cord on the laptop and got on their Wi-Fi, and some kids clustered around a table with me, and they controlled a telescope in Australia and took some images of a star cluster. And then they were able to process that data and mimic, actually what they did is, one girl did it for her science fair project. She watched the light curves of a star over time changing, and it actually was a binary star system that was rotating. And so it was alternating very bright when the two stars were side by side, and then dimmer when the two stars were lined up in our field of vision. And then they would get bright again as they were side by side. So they were rotating around each other and creating a light curve that suggested that sort of rotation. And she was able to create a time series of these images on a star that had not been studied before. And it was really fun. It was original research on a star that had not been studied using high-tech equipment that was halfway, it was across the world from us. And it was something that just generated a visceral sense of excitement in the students to be able to do that. And so then I had some other students get involved too. One of them was particularly, it's a pretty amazing story. His parents are Mexican immigrants who have no more than an 8th grade education. And yet he told me he really wanted to use the telescope. And so I did everything I could to help him along. And he, everything I asked him to do, he did with excellence and total enthusiasm. And anyway, he ended up studying a star cluster using color diagrams, which means comparing the proportionate amount of red and green in a field of stars. And by doing that, he could determine which stars were actually in that cluster and which were in front of it and behind it, and how much dust there was in between us and the star cluster, and also determine the relative age of it through some various methods that scientists use. And I would take him out to UCSB and talk to postdocs there who were very kind and generous with their time. And anyway, he did a research mentorship program at UCSB inspired by that telescope work. And now he's been accepted as a young man at 24. He's been accepted to the PhD program at New Mexico State in astrophysics. And one of his mentors is going to be one of the very same people that helped him at UCSB when he was a teenager with me. So it's a really cool story. And it all came from just not being afraid to eat lunch alone. Anyway, so your topic is about Einstein and curved space, and honestly, this is something that challenges the intuition, because our common experience tells us that we're objects that move around in space and do stuff in a place called space. And our common intuition tells us that we can see things happening at the same time as someone else can. Like my husband across the room, if we both see a bird fly outside, we can agree that bird just flew outside our house just now. We saw it, both of us did, at the same time. That's just our common experience. But the physics of what space and time are suggests that there's something else really mysterious going on there. And Einstein in 1908 and 1915 came up with these, produced these theories for the world of special relativity and general relativity, both of which were just mind-blowing. And they were addressing problems that he saw with Newton's ideas of how mass operates in space. And Newton's equations and laws, Sir Isaac Newton, had developed a description of how mass moves in space using what we would say is our intuitive understanding of there's objects that move in an empty space. But there were some problems that couldn't really be explained by Newton. For example, how is it that a planet can go around a sun at a distance being affected by gravity? How does gravity operate through empty space, quote unquote, empty space? That was a problem that Newton didn't work on solving. He created equations and methods of understanding and predicting the behavior of large objects in space, but he didn't know why they did what they did. And Einstein in 1908 and 1915 came up with some explanations that really were mind-blowing. One of them is that, like, as you can see in your quote for Saturday, March 13th, space-time tells matter how to move. Matter tells space-time how to curve. So what does that mean? First of all, the word space-time, we think of 3 dimensions of space and 1 of time. Well, why are we sticking time in there also? That's the part that Einstein added to the mix of understanding the world that we didn't have before that time. The idea is that how we process and experience time is not absolute. It's not the same everywhere in the universe. There was a metaphysical kind of model that before that time that said the laws of physics are the same everywhere. Okay, well, that's fine, but they are experienced the same way everywhere. That we experience actions, or we observe phenomena in the same way from all vantage points. We can still observe the same thing at the same time. But time and space are tied together in Einstein's theories. They're not separate. So the space-time that I inhabit is different than the space-time of my husband, who's only 2 rooms away from me. So if we see a bird flying outside, from our perspectives, it's actually not happening at the same time, in the same space-time exactly. There is a very slight difference, which we'll never notice. I mean, we will not notice this, but according to Einstein's theory of relativity, our perception of an event is ever so slightly different because we are in different coordinates of this space-time that we inhabit. So it's 3 dimensions of space, up, down, sideways, and deep, and time that are kind of like labels or coordinates for our consciousness to be existing in. And everybody has a slightly different set of coordinates, and that makes it so that we perceive events ever so slightly differently. So that's what's you could think of that as a relativity part, like it's relative. Things that you perceive are relative to your position and the degree of motion that you have. This is the other part of Einstein's theories, which is really interesting, that if you are in motion, your perception of time will be different than the perception of time that someone else would have who's not in motion. Because again, that set of coordinates of space, time for you is different than the set of coordinates of space, time for someone else. Their changing time frame and space frame makes it so that their set of coordinates is slightly different than yours. And so basically, as objects move more quickly through space-time, their time slows down, their perception of time slows down. So if an astronaut were going really, really fast out in space, that person would experience time passing, but let's say they go out to Mars and then come back, and they went really fast, and they come back to Earth, they will have aged a little bit less than if they had stayed on Earth. And this has been something that they've studied, like with twins, like I think it's Robert Kelly, is it? The astronaut has a twin, and he's been up in space he was in space for about a year. And so somebody calculated how much younger he is than his twin. And so that's something that's interesting. You can think about why that is. Actually, there is kind of a geometric way to explain that. I'll try to do that, why it is that time slows down for the person that moves really fast. Because if you think about how do we measure time at all, I mean, the simplest way might be to think of a pendulum clock going back and forth, back and forth. So we're measuring an oscillation, something that goes back and forth. Okay, fine. Well, when it goes to the left and to the right, that's let's say 1 second. Well, if it's also moving like towards the camera, then if you think about it, the pencil, as it moves to the side, if it's also moving forward to the camera, it's actually tracing out not just a straight path to the side, it's creating the hypotenuse of a triangle going towards the camera also. So it's traveling farther as it's moving sideways in order to go to one full side. It's also going forward. So it's actually traversing more distance. And according to Brian Greene in one of his books, where he explains why does time slow down as you go really fast, it's basically that oscillation has to travel farther to get to the other side. And because it's traveling farther, if it's going fast sideways, it will take more time to get to the other side and back. So anything like even a vibration of a crystal that's being used to measure time, any vibration that we use to measure time, to get to the other side, it will take longer because if it's in motion, because it has to travel farther. So that's why the sense of time for a moving person or a moving object, it would experience time in a slower way than another similar object in a space-time framework that was not in motion. So that sounds really strange, but it turns out that has been proven to be true. Because, for example, there are satellites used to keep cell phones in sync with their time, and the satellites that make sure that your phone is correct, that are synchronizing up there, they're using the fact that time is experienced differently on Earth than it is up in space. They use general relativity in their function to make time work correctly on your cell phone. because the other piece of the interesting thing about space-time is that if you were going really, really fast, like imagine this, if let's say you were in a rocket ship and you started going really fast, well, you know, you'd feel this push, right? You'd feel this acceleration. So if you were deep inside of a gravity well, or let's say on a really big planet, heavy planet, you'd be feeling this push down like we do. We feel pushed down to the ground. Well, that's really no different in terms of experiencing space-time than being accelerated. So it's like we're being, we feel, oh, I'm being pushed down to the ground. Well, that's just like being accelerated. There's really no difference. And so if you're inside of a gravity well, time works slower for you than if you're out farther out of that gravity well. So if there's an astronaut in space and an astronaut on Earth, they're going to experience time differently. The person on Earth experiences time a little bit more slowly than it does than the one up in space, because you can't tell the difference between an acceleration and just being in gravity. So that's part of the effects of Einstein's equations on technology, is that the satellites that sync your cell phone to the right time are using the fact that time passes differently on Earth than up in space. Same with the satellites that monitor earthquakes and the height of the Earth after an earthquake. Do you remember, like in Los Angeles, there was this big earthquake? I don't know if you remember the Northridge earthquake. There were sensors on the ground that measured a 8 centimeter difference in the height of the Earth after the earthquake compared to before. It rose 8 centimeters in like one place, for example. And that ability to measure the height difference came from a satellite hooking up to a sensor on the ground and using Einstein's equations to adjust for the fact that time was passing differently. Space-time was different on the ground than it was up in space. So this, even though this seems all very odd and non-intuitive, technology and you know, scientists have been using this actually with our very cell phones. So we can't deny it, even if we kind of might want to. Some of these things are just so strange. You know, it's like, I don't want to believe this. Is too strange for me.
Hey, Kim.
Yeah.
Can I ask, at this point, is it too early for you to explain to us a little bit about this idea of space curving?
Well, yeah, sure, I'll do that right now. So I'm just going to show a video here.
Object's presence within space, curvature affects the motion of other bodies that are moving through that realm. So in visual form, it looks like this. So this is 3D space, a little hard to picture and work with. So I'd like to go to a two-dimensional version that will capture all the ideas. So as you see, space is flat when there's nothing there.
Okay, so what he just did here is, you know, the three-dimensionality, we really have to look at this example as if it were three-dimensional. That's key, because space is not two-dimensional, but the demonstration of like a rubber sheet space is 2D. So
if we bring in a massive body like the sun, the fabric curves. And the Earth too, it also curves the environment around it. And now focus your attention on the moon, because this is the point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. This, according to Einstein, is how gravity works. And if you pull back, you see that the Earth is kept in orbit for exactly the same reason, rolling along a valley in the curved environment that the sun creates.
okay,
That's
so
the beautiful version that will capture all the ideas.
so imagine that three-dimensional.
So, you see, space is flat when there's nothing there. But if we bring in a massive body like the sun.
So the idea is that if space is curved by the presence of matter curves the space. you could have another body rolling through on space-time in what seems to be for it a straight line, but like a marble rolling on a trampoline, if there's a bowling ball in the middle of the trampoline, that marble is going to be thinking it's rolling straight, but actually it's going to be following a curve and end up rolling around the larger object. So I'll just, now watch this part again, only imagine it's three-dimensional. Okay, so just try to insert one more dimension in this grid.
Fabric curves. And the Earth, too, it also curves the environment around it. And now focus your attention on the moon, because this is the point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. This, according to Einstein, is how gravity works. And if you pull back, you see that the Earth is kept in orbit for exactly the same reason, rolling along the valley in the curved environment that the sun creates.
So that's in a nutshell. I mean, that's the easiest way to imagine it right there. So it's no longer that we live in this grid that's stable. We have to reconceptualize our experience as time and space are really relative and in motion and fluctuating, expanding, contracting. They're not this kind of stable grid which we walk around in. So in terms of our awareness and imagination about space and time, it does allow for quite a bit more of an expansive sense. Now, Joe actually had some very interesting comments about the ideas of space, like related to music, and I think it would be interesting if he could share them right now. Would that be okay?
Yes, absolutely. That would be great. Would you like to introduce Joe?
Oh, yeah, Joe is a very brilliant person who understands quite a bit about music, and he's a poet and a philosopher and a playwright and a musician, and also my husband.
Thank you. Joe?
I mean, I was talking about in the arts. I mean, you know, there are correlates for what we imagine to be space in ordinary experience. So, you know, for music, for example, there is tonal space. I mean, you know, music creates this inner world of sound, a kind of a universe that is filled with motion and form, involving you know, various dimensions of abstract space. In fact, we use intuitively the words to speak about a high tone or a low tone, as if there's some spatial direction to these things. And of course, then there's a spectrum of timbre as well. That there's the really reedy instruments, and then there's the more mellow, oh, you know, I mean, there's the same tone. I mean, what's the difference? It's the same tonal space, but then it's varying the timbre space. So there's different ways in which timbre is played with. So, and then of course there's rhythmic space as well. You can slow down or speed things up, which we think of as time, but actually intuitively or aesthetically, it occupies a kind of dimension of space. So, you know, a good orchestral composer is playing with these different dimensions of space in these abstract dynamic forms that we call music, in order to communicate emotions and feelings to us. So anyway, that's what I had. But I wanted to ask him a question then. You know, my understanding is, and from what you've said, is we speak about the relative frames of reference, that there's the way there's differences of experience. Like one of the things you said was that the astronaut who leaves experiences time differently, but doesn't he experience time the same? But when he comes back, I mean, his watch to him is still going the same speed and all of that. But when he comes back to Earth and he compares it with his twin, something else has happened, right?
Yeah, actually, that's probably a better way of putting it. That I mean, from their own perspective, they think everything's normal, but their time, if they're up in space, is faster than if they're down in gravity. Okay, actually, if you're moving very quickly, time will pass more slowly for the moving person, but they experience it as if there's nothing changed. But when they come back to Earth, many, many years have passed, or more time has passed. So that's if someone's moving, time slows down for them. Also, if someone's inside of a gravity well, time is passing slower for them than if they're outside of a gravity well. There was
Okay.
a movie that showed this pretty well, a science fiction movie several years ago. I forget the name of it, but they used actual physics principles in it, and they showed astronauts traveling really, really fast out at somewhere like half the speed of light in space, and then they would communicate with people back on Earth, but those people were aging faster than they were, than the astronauts.
One other quick question, Kim. When you say that, for example, a twin leaves and travels around near the speed of light, and he comes back and he finds he's aged slower than his twin, isn't that giving, to my mind, isn't that giving a kind of absolute position to one person over the other? Like, why, if we're disinterested in their relative motions, why should we assume that the one person is moving faster than the other? From his position, right, the other person seems to be moving. Why isn't it go the other way? I don't understand that.
Oh, you mean like, why do they think, okay, who's moving away from whom?
Exactly, and who's moving fast? I mean, maybe the whole person who's staying at home, his whole frame of reference, including the Earth, maybe that's the thing that's actually moving close to the speed of light, and then the other guys. I mean, it seems to me we're absolutizing one position or another, and that seems to me different than relativity.
Well, I think it could be also that the astronaut that's in space is not in the gravity field of Earth. They're kind of creating their own acceleration field. They're by accelerating their spaceship and moving close to the speed of light, let's say. I think that it has to do with the amount of acceleration, the change in space-time. It's not just space-time itself, it's the rate of change of space and time. And yeah, the frame of reference, you have a good point there about that. I don't know, but I do suspect it has to do with acceleration. So there's, my son-in-law could answer this.
Can I ask another question, Kim?
Yeah.
I know you've learned about this probably fairly early in your life. Nevertheless, I wonder, how has your way of living your life been affected by understanding things like space-time and the curvature of space? How does that affect your daily life and how you think about it, how you operate in the world? If you can think back to that time before you understood these things.
Yeah, well, it gives you a sense of fullness and abundance in space and time, because it's not what you think it is. There's more, basically. There's a plenum in space and time. There's an abundance of possibilities that our senses don't reveal. So when I look at just, stuff in space, I can actually think of quantum foam, even if I want to, or the curvature that mass provides to space-time. I mean, that's fascinating. And it also gives a potential for an awareness, conscious engagement with things in a creative way that I could see the world differently. So I think it was just a freeing sense of potential.
Let's see. So where you may have perceived nothingness in the past, you're seeing maybe well, they talk about the fullness of the seeming void.
Yeah.
You've got a richness in what might seem otherwise empty or nothingness.
And an interconnectivity, like the idea that all things are connected, and intimately so in the fabric of space and time. So an action in one portion of the field instantly will be affecting another portion of the field, because it's all the grand sum of things mathematically. If you were able to sum all the energies and all the positions in space and time together, then one might be able to understand the motions of everything. But I mean, that's something beyond us. But it does lend philosophically a sense of interconnectivity, unity, a radical unity.
I see. Because as one thing shifts in the universe, then that causes a curvature around itself that's going to ripple out and affect something else that'll affect something else, because it's a fabric, an interconnected fabric.
Yeah, like in dance, like if you're having one person moving a certain way in dance, then that might affect someone else in the dance group, how they want to carve out their space.
Mm-hmm. Yeah. Yes, I can see how that could happen. David, I think you were leaning into your screen in a way that meant you were just about to bust with a question.
It's just reminding me of my favorite quote from Einstein, that coincidences are God's way of staying anonymous. That everything that happens is affecting everything else. And I think until you expand consciousness to realize that that's true, you'll simply see things as coincidences rather than as the interconnectivity of all things.
Beautiful.
I was looking at Kim, as you were giving that description, I'm looking at the background that you have of the waves coming in. And I was thinking, if you were traveling along at the same rate as those waves, given that the waves weren't ever going to break, the wave would look like it was standing still. If you were moving at that same rate, it would actually be standing still. And if you were moving even faster, it would look like the waves are moving backwards. Is that similar to the idea that we're talking about?
Well, it's related. Yeah, you could say that.
And then also the image of the trampoline and the ball moving around the trampoline. I imagine myself from the perspective of the moon, looking at the trampoline from the perspective of the moon. It would look like straight lines.
Yeah.
Because I was having that perspective. But what we saw was a third perspective looking at it from a distance.
Right. Yeah. And then also make that trampoline be three-dimensional somehow in your imagination.
Then you lost me right there.
I know. That's the thing we always have to do, is just try to be flexible with that it's not just two-dimensional space, it's actually space-time. 3 dimensions of space and 1 of time that's curved.
This has to be so good for our brains. I'm sure we're going to be less demented for a longer period of time by even considering these ideas.
Kim, when I try to think of three-dimensional space, I can't help but go back to the classic symbol of space, which is water or the ocean. Because then you can feel that, it's all around you. And then you, like, how would it be curved for one? Like, then I think of currents, like you get caught in a current and then you're brought around. But then I was wondering then what physicists think space is.
Well, I'll get back to you on that one. But, maybe this helps. Like when physicists try to explain multidimensionality of space, for example, in string theory, the theory of the very tiny, small it requires an 11-dimensional space-time in order to have string theory work even. And, so you say, well, what does that mean? They say, imagine another quality in space. So imagine a 3-dimensional grid, or imagine being immersed in water, let's say. Now imagine another quality in the water, like maybe that 4th dimension of the 3-dimensional space, but now let's add one more dimension. That would be maybe temperature of water or color of water, temperature and color of water as you're immersed in it. So that might be kind of an analogy of developing more dimensionality of space for your imagination exercises. And then, well, physicists, the best I know, they'll come up with some equations to tell you what space is. If you want them to, they will. But that doesn't really help. So then, in the classic mechanics idea, space was like we intuitively think. It's a place for things to happen. But it's a flexible notion now with Einstein's theories of relativity. It can contract and it can expand. In fact, if you look at the light coming from stars, everywhere, every single star we see has a wave form that has been shifted towards the longer wavelengths. Basically, if you look on Earth at, say, a neon light, or better, let's say pure hydrogen in a bulb, and you look at its spectra, you can see it emits, when you put energy through it, it will emit very strongly on certain nanometers of light. So you can say, oh, hydrogen emits at 620 and 680 very strongly. Well, when you look up at stars in space, you can see the same spectral lines, only they're not at 620 and 680, let's say, they're at 640 and 700. So those same spectral patterns are shifted towards slightly longer wavelengths. And the farther the star is, the more there is a shift. How can that happen? Well, scientists say that's because space itself is expanding. And there would be one other explanation, is if we were at the center of the universe and everything was expanding away from us. So, if you wanted to believe that, you could, but scientists would say that's so unlikely. The only other explanation for what they're seeing with this, basically it's called redshift, is that the whole entire space framework must be growing. And then you ask, well, what's it growing into? And like, you can't answer that. You're just like kind of not allowed. It doesn't make sense. So I don't know, but the idea of space itself is expanding is another aspect of modern understandings physicists have of what space is, that it is expanding right now. And that's shown by the redshift of stars and the fact that more distant stars have a more distant redshift, which means they're expanding at a greater rate of acceleration. So it's the accelerating inflationary universe.
Fascinating.
So Kim, just to be clear, normally when I hear about the expanding universe, I'm thinking of the objects within the universe are diverging, but you're saying something different. It's not the objects in space that are diverging, it's the space itself that's changing, that's expanding.
Yeah, the common example is if you put raisins in a bread dough and then you cooked the bread dough, every little raisin in the bread dough would go with the dough, and as the dough expands, the raisins would go apart from each other. They'd all expand because they're part of this inflating mass of bread dough becoming a bread loaf. Those are analogous to stars in space. As space expands, those stars spread apart from each other because their medium that they're in is expanding.
But we would have to imagine the raisins expanding too.
Well,
not just getting farther apart.
yeah. Oh, okay. I see what you're saying. I don't think so, but I don't know.
That's very good, man. That's really good.
We'll all be
Is-
giants.
Is there a, is there a center?
Well, that's the thing. It's like Emerson says, you know, God is a circle whose center is everywhere and circumference nowhere. Did I quote it correctly?
Yeah, but it's not Emerson, but go on.
Oh, well, no, there wouldn't be, from what I understand. This is where our concept of space just gets blown away. You know, the whole thing is expanding without a center, even though in theory, like if the Big Bang would have been from some, you see, you can't say the Big Bang started in a point because that's a point in space.
And
So-
space itself came into existence
Yeah,
with the Big Bang.
yeah,
So the Big Bang didn't happen anywhere because there wasn't awareness yet.
yeah,
Awareness came into existence with the Big Bang.
yeah. So thanks, Einstein.
So who was the quote by, Joe?
Oh, wait, gosh, it's an old quote. I think there was first a Greek philosopher. Many people have said it, Nicholas Akusa. God is a circle with center everywhere and circumference nowhere. Actually, Emerson in one of his essays does repeat it, so Kim's not wrong.
So what's most intriguing about this topic of expanded views of space to you? Can I hear from everybody? What difference does it make in your life? The same question Renee asked me. I turned to the participants.
Mary, do you want to kind of lend a voice here? Brand new, right?
I can lend a voice, but I have no idea. But it's really exciting, just listening to the ideas and to see on the various demonstrations of expanding and contracting, and so it's really exciting. I thank you. I don't understand, but it's exciting.
I think watch the video that I sent on that chat link. It's quite good.
Well, I have a question I've been saving up for you. And it's the reason that in the almanac, I called it curving space, carving space. And it is my experience from having danced Nia that I experience with my mind carving space actually in a certain outline, in a certain shape, and then filling the space that I have carved in an image with my body. So like I see it, I fill it. And the founder of Debbie Rosas has a quote that I like to use in the almanac. It probably gets in there every other year. She says, when I intend, my energy body precedes me and sucks the rest of me along. Something to that effect. And I wonder if that is in any way that you can see connected with this idea of, you know, bodies traveling, creating curvatures that affect the other body's movement around them and so on.
Maybe if a person has a kind of a metaphysical understanding of human nature that includes multiple levels of being on different planes, then yeah, what you're saying has a potent analogy for on the more invisible, well, the non-physical energy planes with will and intention. If someone is going into that space, then with the invisible aspects of a human incarnation, then the physical will follow. In terms of physics, well, there is the idea of energy in string theory, at least. That's a whole nother topic, but it's a theory, it's only theory at this point. It's not at all had any demonstration of being proven, but it could predict a lot of things. It suggests that vibrations, very, very tiny vibrations, then affect or create actually mass and energy. Every bit of the universe that we know of is created by vibration. And the things that are vibrating are, we're not supposed to ask that because it's so mind-blowingly different than what we might think. It's not a thing that's vibrating. But vibration itself at the very tiny, tiny Planck scale of 10 to the minus 35 centimeters, which is like 0.0000, like 35 zeros, and then a 1 centimeters big. So it's extremely small. So maybe that's a correlate in physics, in the realm of physics, to what you're describing, is the idea of string theory.
Thank you so much. Maurice?
I have this conversation every 10 years with the Miller family, and they're very polite, and that's all I could say, but I'll say it again. So if you consider space to be your position in an organization, your role, you're the assistant director of something, and you get your boss gives you a real assignment. And a real assignment means that the boss has some idea of when they expect you to complete it. Then you're operating on two philosophical definitions of time, or two definitions of time. So now you're into 5 dimensions. One is chronological time, right? We all agree, you and the boss agree, it'll take 2 years to complete this project. Okay? So that's chronological time. But then there's also subjective time. That is, it's not just the time that we all know as clock time, but the time of intention, because the boss might change their mind. Or as Kim pointed out and others, something else is going to come up and maybe you're not even going to do the project, it'll take 3 years. So you have clock time, which I think, correct me, is chronos by the Greeks. And then you have the time of intention or intentionality, which is kind of the time of flow of consciousness where things change and move and all of a sudden. So maybe Joe can help me here. But I think what I'm trying to say is that time itself is more than 4-dimensional because it certainly involves our intentionality, which is what we were talking about with all this energy, with tiny vibrations, creating mass and energy, creating things coming. So there's some kind of intentionality, which is different than just mechanical clock time that you see on the wall. So that's all I'm going to say, but it's kind of intimate because if your boss and you don't have, if you're not on the quote, the same page in time and space, the fur is going to fly. So it's a very intimate actuality to this subject. It's not as abstract as we think it is, but maybe one of the Millers can help me out.
Well, if I could say something that kind of leads into, before we started, I looked up a poem by Rainer Maria Rilke about curved space. And what Maurice has just said kind of leads into it, because what Rilke is talking about is this whole idea about being thrown a curve. You know, we use this expression to imply that there's, gosh, I'm getting an echo. Kim, is that you? Sorry. it's kind of hard for me to, I should shut off there's when we get thrown a curve, it means our intentions are different. If we imagine our intentions to be like straight shots, to be thrown a curve is to be thrown into something we didn't intend, and it seems to require us to gain our footing in a different way. And he has this poem about where he compares it to catching, like catching a ball. And he says we can only feel equal to the game, equal to ourselves, equal to our potentials, equal to the universe, when we sort of throw ourselves and abandon. And I just now saw there's an owl sitting on the tree out there. It's quite remarkable. So anyway, this is what he says. This is Rilke's poem in translation. In merely catching your own casting, all's mere cleverness and indecisive winning. Only when all at once you're catching balls, an everlasting partner hurtles spinning into your very center, with trajecture exactly calculated curvingly, recalling God's stupendous pontifexture. Only then catching's capability, not yours, a world's. It goes on from there. But I love that idea of this somehow to allow the universe to throw us a curve, because we so much want to grow in our own throwing and our own catching.
That's beautiful. Thank you so much. We have reached and gone slightly past the top of the hour, and it has been a marvelous hour for us. Mary, can I call upon you to give a vote of thanks? Would you feel up to doing that for us today?
Sure. Well, thank you both, Kim and Joe, and all of the contributions to this topic, which is certainly exciting and certainly out of my comfort zone, but it's all good. And I thank you, and the group thanks you for certainly stimulating our ideas and pushing us towards new things.
Well, I want to, before we depart, let you know about next week's topic. We have a wonderful local singer-songwriter, which Joe actually is over in Santa Barbara. This is someone on our island who is going to take up the topic of jamming and riffing. Jamming and riffing. So those are musical terms, and we're going to see how that will apply to not only the world of music, but analogically to our lives. So we're looking forward to that also. So thank you so much, Kim, and to Joe as well. Fascinating and stimulating. Thank you so much.